In the previous chapter, you learned how to graph inequality for linear inequality. Now we're going to talk about system of inequality. Remember, system means a set of two or more. So let's look at this first question. Solve the system of inequality by graphing. So this first one says x plus y is greater than or equal to 7. So what we want to do is first change it into y equals mx plus b form. And then we are going to graph that line. We call that boundary line. So we're going to start at 7, and it has a downward slope of -1. This is going to be a solid line because it's greater than or equal to. So the equal to makes this a solid line. And then this one says greater than, so we're going to shade up. So if you're not sure how to shade, what you can do is two things. If it's greater than, you're going to basically think of it as this line cutting this region, this 2D region into first one and second one. So you're going to pick the higher one. If that is very confusing for you, then you can also plug in a number. So for example, 0, 0. You're just checking to see if 0, 0 is part of the graph. So you put in 0 for x and then 0 for y, and then you check to see, is that true? No. 0 is not greater than or equal to 7, so you're going to shade the side that does not have 0, 0. All right, so we're going to do the same with the second one. I'm going to do that in a different color so you can see it better. Okay, so 2y is less than or equal to minus 5x plus 20 divided by 2. Y is less than or equal to negative 5 over 2x plus 10. So this one we're going to start at 10. I should have made more points there or make the graph a little bigger. Down 5. 1, 2, 3, 4, 5 over 2. And then down 5 over 2 here. Okay, notice how this is also a solid line because of the equals to. And then this one's less than, so when we divide this region in half, we're going to shade the less than or the bottom one. So the question is, where is the answer? So some people say, this is the answer. This is where they intersect. That is incorrect. That is the answer if the question were just equal to. If it were this one equal to this, if you just had two equations, and remember equations means there's an equal sign. If you just have two equations and then you're solving the system of equations, then that is the intersection is the answer. But this question is an inequality, so then they're saying where do all the numbers fit in this region? Then that would be where they intersect, which is this part. So every number in this shaded region will work for both of these equations. All right, so let's go ahead and have you try one. So solve this one on your own. All right, go ahead and check your answer. So this yellow region is the region that solves this inequality. Just make sure the first equation is a greater than sign. So you need to have dotted line instead of solid line. All right, let's look at other kinds of inequality. So this first one is a absolute value. So let's try this one. Y is less than or equal to 3. Less than or equal to 3. Y equals 3 is the horizontal line at 3. So less than or equal to 3, that's going to shade down. The second one is a absolute value. So just a reminder of how to graph absolute value. First, find the vertex. The vertex is at 1, 0. This one has a positive slope of 1, or what we kind of call slope of 1. This is a greater than, so dotted line. And this is greater than, so we're going to shade up. So the question is, where is the solution? Right here. Okay, let's have you practice this one. Please go ahead and check your answer. This one, the only region that's intersecting is this very small part. All right, now let's bring it together. We're going to look at a system of inequality, but with word problem. So let's look at the question, first one. Your city's cultural center is sponsoring a concert to raise at least $30,000 for the city's youth services. Tickets are $20 for balcony seats and $30 for orchestra seats. If the center has 500 orchestra seats, how many of each type of seat must they sell? Each type of seat. So again, look at the question stem. So it's asking for how many of each type of seat. So the number of seats is what we need to find. And there are two types of seats. One is a balcony seat. So we're going to put an X there. The other one is the orchestra seats. So we're going to put a Y there. So we're going to create a system of inequality to represent the information that they give us. First, it says that they have to raise at least $30,000. So that has to do with cost. So you have $20 for each balcony seat, and then you have $30 for each orchestra seat, and then you want to raise at least $30,000. If the center has 500 orchestra seats, so what does that mean in our equation? Does it mean Y is 500? No. So what does it actually mean? It means that you have at most 500 orchestra seats. So should I write it like this? Y less than equal to 500? Well, that's closer. So, okay, so if you're kind of wondering, why are we not writing Y equals? Because no one says you have to sell all 500 seats, right? You could have a lot of people who don't want to buy orchestra seats. But no matter what, you can't sell more than 500 because you only have 500 orchestra seats. So if I write it like this, does it make sense? Not quite. Remember, you can't go below 0. You can't sell negative number of seats. Okay, so this is my system of inequality. Now what I'm going to do is graph all the possible places that this works. So let me graph the easiest one, which is Y is between 0 and 500. I'm going to shade here between 0 to 500. And then the next one, this one is a little bit annoying because the numbers are so big. Again, different color. 30y greater than equal to minus 20x plus 30,000. Divide by 30. Y greater than equal to minus 2/3 x plus, let's see, 1,000. All right, I'm going to start at 1,000 and goes down 2 over 3. All right, so some of you may be a little bit confused on how we're going to graph down 2 over 3 slope because my points here are in terms of, what is this, 100, right? So down 2 over 3 just means down 2 units over 3 units. As long as the units are the same, it doesn't really matter if you're doing down to whole numbers or down to 100 or down to 1,000, as long as the units are the same in the x and in the y. So in this graph, the units are all in terms of intervals of 100. So it's okay if I just go down 2 over 3, meaning down 200 over 300. I'm going to get the same if I were to say down 2, like the actual number 2 and over 3. Anyways, that was a long explanation. So we're going to get the same slope if we do it this way. Okay, this one is greater than equal to, so we're going to shade up. All right, so where is the solution? That solution is somewhere here. So anytime I have an ordered pair that's in that region, it will work. And then because this is a real life problem, we're looking for integer solution. So any integer order pair inside that shaded area will work. All right, let's go ahead and have you pause the video and try this one. So go ahead and write down your system of inequality first. Check your answer by playing the video and then graphing it. All right, did you get the correct inequalities? So if you did, continue and finish graphing. All right, go ahead and check your answer. The yellow region is the solution. Notice how I did not color lower than the x-axis because I want to keep my numbers real, right? Because we can't buy negative toppings. So I'm saying that x and y have to be positive numbers, 0 or positive numbers. So 3.4, we're going to go into something called linear programming, which is using the information that we just learned from the previous section. And then this time, instead of just 2 equations, we're going to graph 4 or more equations into the same one, just so that we can solve some word problems. Let's look at this first example. It says graph the system of inequality, and we call that constraints, and name the vertices in the feasible region. Which vertex maximizes the objective function? Wow, that's a lot of information. So first, we have so many new words that we have not seen before. First, constraints, vertices. Maybe you know vertices, maybe you don't. Feasible region, maximize objective function. So there are a lot of things going on, but let's go ahead and do what we know, which is graphing this line. All right, so this one becomes y less than equal to negative 1/2 x plus 5/2. So let's go ahead and start graphing this line. So we're going to start at 5/2, which is 2.5, down 1/2, down 1/2. And this is a solid line. And less than. Okay, we have 4 lines, so I'm going to try to use 4 colors. This one is y greater than equal to x minus 2. So all I did was really mentally put the y on the other side and then move the 2. So start at -2 and go up 1/1. So I know that my graph is not perfect, so I'm actually not going to rely on my graphing to give me the points. I'm going to have to think about this later, but anyways, this is kind of how you graph, and then this is greater than, so I'm going to shade this side. All right, the last two says x greater than or equal to 0, y greater than or equal to 0. This part just basically means quadrant 1. Okay, oops, I forgot the T. So if you don't remember the quadrants go from top right, so quadrant 1, quadrant 2, quadrant 3, quadrant 4. So both x and y greater than or equal to 0, that just means quadrant 1, including the x and y axis. So the region that is enclosed between these 4 constraints is this part. Okay, so from here, let's go ahead and kind of explain the new terms that we have not learned before. So you can see that this this region, okay, first of all, this region has a name. This region is called feasible region. Feasible, if you remember, in English means possible. So this is the region where all the possible answer is. Okay, and then in this region, it has 4 corner points. It's enclosed within 4 corner points. These points, we call them vertices. Vertices is plural for vertex. Vertex is the singular word, noun, sorry. Then constraints. Constraints is just what is constraining this region, what is creating constraints on this 2D region. So the constraints are what we call the inequality. So this is the constraint or constraints. And then the last part, or actually two more, objective function. Objective, if you kind of remember in English, objective means the goal, the purpose. So the purpose is that we want 2x plus y. So this is the objective function, 2x plus y, whatever that means. We want to do what to the objective function? We want to maximize. Whatever answer we get, we want that to be the maximum. So we want the maximum 2x plus y is what it's saying. All right, let's go ahead and solve this problem. So what's going to maximize the objective function, 2x plus y? Well, everything in this feasible region works because it fits all the constraints. It fits all the constraints. But not every number, not every combination will give you the maximum, right? Because maximum usually means there is only one pair of x and y that's going to give you the maximum, the biggest number ever. So how do you pick? This region is quite big. You got so many numbers in there. Which pair is going to give you the maximum number? Well, it only depends on the vertex, the vertices. The vertices are the only ones that's possible to give you a maximum or minimum. So we're only going to check the vertices. So here's what I do. I make a table of the vertices or vertex, and then I put the objective function, 2x plus y. So what are my vertices? Well, I know one of them is 0, 0 for sure. I think the other one is 2, 0. Right, this. And then I know the other one is 0, 2.5 because that was my y-intercept. And then I have this last one that I'm not quite sure. If you graphed better than I did, you probably figured out what it was, but I did not graph very well. So the question is, where is that? Well, remember in the previous section, this point here is the intersection between the red line and the blue line. The intersection between the red line and the blue line. So the question you ask yourself is, how do I find that intersection? How do I find that intersection? It's basically, if you were to take the blue line and the red line and you made them equal to each other, basically in the previous section we solved this 3 ways, right? Graphing, substitution, or elimination. So those 3 ways help us figure out the intersection between 2 lines. So you're going to use any of those 2 ways. Graphing for me at this time was not a good idea because my graph was not good enough. So I'm going to take those 2 lines. Instead of using the inequality, I'm going to look at just the line itself. So I know the blue line is y equals. So I'm going to change that to an equal so I can solve. And then the red line is a y equals x minus 2. And since they're both in terms of y, I'm going to basically use substitution. So I'm going to substitute this into this y. So x minus 2 is negative 1/2 x plus 5/2. And then I'm going to solve that. So I'm going to add 1/2 x to the other side. That gives me 3/2 x. And then if I added 2 to the other side, I get 2 and 5/2, which is 9.5. And then I'm going to multiply by 2/3 on both sides. That gives me 3. So x is 3. And then I'm going to go back into any of the 2. This second one looks easier to find. So I'm going to plug that in. So y is equal to 1. So that means it's telling me it intersects at 3, 1. So if you ever have a case where you cannot figure out the vertex and you know which 2 lines intersect, then you can use a system of equations to solve for that line. Next, we're going to check these 4 vertices to see which one maximizes the objective function being objective function being 2x plus y. So first one is 0, 0. If I plug it in, I just get 0. The second one, 2, 0. I plug it in, I get 4. The third one, I get 2.5. The last one, I get 7. So I can see that 3, 1 is going to maximize. So let's fill in these parts about the vocab. So constraints means the equations of limitation. So the equations that limits, like everything in here will actually work if you're staying within this limit. And then the implicit constraint. Implicit constraint are these ones, basically saying that implicitly, like even if I don't tell you, you would know that these constraints are true. So this is kind of like a non-spoken constraint, maybe. So you know that if the question is asking you for like how many pencils and pens, you would have to say it has to be positive number or they have to be integers. So that's the constraint. You cannot actually have negative pencils, right? So that's called implicit constraints. Feasible region means the area of the graph that satisfies all the constraints. The objective function is the goal of the problem. And that means what you're trying to maximize or minimize. And then the vertices mean the corner points of the feasible region. And these are the usual points that you would check in the objective function. So let's just look at how to solve these first before we actually move on to word problems. Let's look at this problem. Graph the system of inequalities, that's constraints, and name the vertices in the feasible region. Which vertex minimizes the objective function p equals x plus 3y? So let's go ahead and actually graph this one. So if we were to solve for this equation in y equals mx plus b form, we would get y is greater than or equal to, so basically try to do this in your head, minus 1 over 2 x plus 7 over 2. 7 over 2 is basically 3/2. So I'm sorry, I said 3/2 right here. And it goes down 1 over 2, down 1 over 2. And then we draw a straight line through. And then this is greater than. So we're going to shade up. Okay, and then the other one is x is greater than equal to 2. Change this color. Greater than equal to 2. So we're going to be here. And then the third one is y is greater than equal to 0. So it's going to be this one, shade up. This is very busy, so you might want to just do this in your head instead of like what I'm doing is too many colors. Okay, so you can see that the overlap is like this region here, the yellow one. All right, let's talk about vertices. So we know we're trying to find a vertex that minimizes the function, and the function is, our objective function is x plus 3y. The question is, where are the vertices? This is very tricky for a lot of people because when we're looking at the previous question, the feasible region was contained within a shape, like some kind of polygon, right? And we can find the corner points really easily. But this one, if you're saying that the feasible region is this one, that would be partially correct. The reason being, this part is not true. Because the way the graph is drawn, I only put in a graph paper that extends to about, positive 9 to positive 9. But your graph will actually keep going. So then what happens is that this graph actually keeps going forever, right? So then this is actually just saying that your graph is not contained within a polygon shape. It's contained on one corner, right? This corner only. And then the other side just keeps going forever. So then the question is, well, then how do I find a vertex or vertices? It's just going to be the corner points, these two only. Please don't create your own vertices elsewhere. It doesn't make any sense. Your feasible region is not contained. It's only bordered on 3 sides only. So please be careful of this one, of ones that goes on forever. Okay, this point here, I want to say it's 7-0, but I'm not really sure. So remember, how do we do that? How do we figure out what that actual point is? We take this blue line, and then we say, where does it intersect with the green line? The green line was y equals 0. So then we're saying, when is y equals 0 intersecting my first equation? Well, that is just a question of when is x plus 2y equals 7. Notice how I write equals 7 instead of greater than equal to 7, because we're actually trying to figure out the intersection of 2 lines, not 2 inequality. And then when are these 2 equal? So this is a very easy substitution question. So plug it in. So x is 7. It is 7. So 7-0. All right, the other vertex is this one here, which is intersection between the red and the blue. The red is x equals 2. So that is the intersection between x plus 2, y equals 7, and x equals 2. Oh, that's a nice, easy question to solve. So 2 plus 2y equals 7. 2y equals 5. Y is 5 over 2. So this is 2 comma 5 over 2. Those are the only 2 vertices. And then we would basically try to solve this one. Let's see. Putting in 7-0 in the objective function, you get 7. Putting in 2 5 over 2. This one's a little bit harder. 2 plus 3 times 5 over 2. That is 2 plus 15 over 2, which is 4 plus 15 over 2. That is 19 over 2. 19 over 2 is about 9.5, or not about, it is 9.5. So which one minimizes? It's going to be this one. All right, let's go ahead and have you try this one. What point in the feasible region maximizes p for the objective function 2x plus y? So go ahead and graph it and solve it. All right, go ahead and check your answer. The answer is 3, 1.